Here's Chapter 6, Section 2. At the top there, I reminded you of a few formulas that are easy to find, but nice to remember the formulas for the volumes of these shapes. If you have a sphere with a radius r, the volume is 4/3 pi r cubed. A cylinder with a radius r and a height h, pi r squared h. And a rectangular solid where it has an area, which is base times height, but just to leave it as an area, the volume is the area times the height. And that fits with that cylinder because the area of the circle is pi r squared. However, now we're interested in volumes of rotation. So now that is something very familiar because you'll have seen light bulbs. A light bulb is a good example where the volume is a volume of rotation. It's not a perfect sphere. Here's a water bottle. It has a volume of rotation instead of being a perfect sphere. So here's how we do it. You start out with a type 1 or a type 2 area, just like we've been working on finding the areas. And then you're told that it will be rotated around an axis, a straight line. So for instance, here is a volume created by a type 1 region rotated around the x-axis. The type 1 region is first shown there, has a top function f, bottom function g, goes from a to b. And in the middle, here's what it looks like when you rotate it around the x-axis. It goes all the way around, makes perfect circles, although drawing them in perspective makes them look like ellipses. It comes out of the plane towards us, and then all the way down to a perfect mirror image of itself at the bottom, and then all the way back into the plane and into the distance until it gets back. And we're interested in the volume that the shaded region sweeps out. So it'll make sort of a funnel shape that has a hollow core. Now, here's how you do it. You look at a slice, just like we sliced before to find the area. And for a type 1 region, that's a vertical slice that I've shaded in real dark there. It goes from f of x on top to g of x on bottom. And we just keep track of what happens to that slice as we rotate the area around the axis. So there's what happens to the slice. You can see it both inside and then separated out. It sweeps out what is basically a cylindrical solid, but with a hole in the middle. We call it a washer, like a washer that you'd put on a bolt. And another picture of it down here that's a little easier to see. All right, that is a small volume. The thickness of that slice was, in this case, dx, and so the volume will be the area that it sweeps out times dx, the thickness. Now the area of that cylinder with a hole in the middle is going to be a pi r squared minus a pi r squared, and there are two radiuses. There's the big radius and the small one of the hole. So we want pi r1 squared, that's the larger radius, minus pi r2 squared, that's the small radius to get rid of the hole. That'll give us the area of that, like the surface, the top, or in the picture it's the left area of that washer. And then the thickness of the washer is going to be our dx, so that'll give us the volume, and we call it dV because it's a small volume, a little tiny volume that we're going to now integrate to get the whole thing. So the radius 1 in our picture is f of x because it's the furthest function from the x-axis, and radius 2 is g of x, and those are going to change from left to right as you go from a to b. Those radiuses are going to be different. Every single washer is going to be a slightly different volume. That's how we can all add them up with an integral. And you can factor out the pi because pi r1 squared and pi r2 squared both have a pi in it. So you pull out the pi and you're left with the two functions squared and then subtracted. Notice that squaring happens before the subtraction. So you can't square the minus sign and make it a plus. We're going to need some parentheses in these. All right, here's the formula for the whole volume. It's going to be for the integral from a to b of that dv. And dv is pi times f of x squared minus g of x squared.